Okay, so now we're going to start Chapter 5 in Circuit Analysis 1. This chapter is about op-amps. And there's two pictures of op-amps that I'm showing you right here. This one's called a dip package. That's what you're going to be using in the lab. And this one's a surface mount package. But anyway, op-amps. Whoops, come over here. So it's an electronic device, but it basically behaves like a voltage-controlled voltage source, which you're already familiar with from your homework problems. But it can also be a voltage or current-controlled current source, so it can supply current as well. It's called an active circuit. Actually, op-amp is short for operational amplifiers, but it's an active circuit element, and it performs different kinds of mathematical functions in the circuit. It can add voltages, subtract, multiply, divide, do differentiation and integration, which we won't do till next chapter after we start using capacitors. So your book never defined active circuit, but active circuits are circuits that can generate energy. They output more power on the signal than the input signal power. But that's because they are powered devices. So it's not like I'm creating energy. Passive circuits are like your resistors, capacitors, and inductors, but they only dissipate energy. They are not considered active circuits. And they are also unpowered. So they are unpowered and they don't output any more power than what was put into them. So we have here on the right hand side, this is a circuit, the schematic symbol for a single op-amp, but the op-amp is in some kind of a package. Here's an example, a package outline. Actually, you'd call that a footprint, with the pins labeled on the device. So the pins, notice the order that they're labeled, 1, 2, 3, 4. 5 is on the other side, 6, 7, 8. And you can identify which pin is pin 1 by either finding the notch on top of the device or the dot on top of the device, and that identifies which is pin number 1. So if I go back to my picture, this one doesn't have one, I think because it's a surface mount. It was probably very tiny. But this one does. I can see that there's a dot, and that would be pin 1. Oh, that's a little disturbing that that one doesn't have one, but okay. This is a 8-pin package, and it has one op-amp inside. You can also have 2 op-amps in one package. So when you do the lab, I don't know if you're going to have 2 op-amps or 1 op-amp in your package, but we'll be doing labs with a kind of a general purpose op-amp called an LM741. It's a garden variety used in lots of things op-amp. So op-amps must have power to work. So if I look at the pins, here's the schematic symbol. These pin numbers, 7, 2, 3, 4, 1, 5, they relate to the package layout here. So you see that you have a plus voltage. For your 741, it's probably going to be like plus 15 volts. And your minus voltage is going to be minus 15 volts. We may or may not use these offset nulls, but we will use the inverting input, which is pin number 2, the non-inverting input, pin number 3, and the output is pin number 7. So you see inverting, non-inverting inputs, and outputs. So I wanted to show you a little bit more some of the packages that you could possibly find for op-amps. So I have a kind of a nice web page that showed you some of the packaging. So just learn about electronics, but if you see down here, they show you a bunch of different packages. We do have in the lab the DIP package, pin 1, which means dual inline package, and we have this CAN package number 3, which is also called, there's an outline for the CAN packaging here. This is a TO5-8 package. So it's just names of different kinds of packages. In the lab, I will try to show them to you, the different packages, so that you can see them. This is dual inline DIP package. And my picture doesn't have a surface mount on there, but okay. What else? Okay, so if you put a voltage into the inverting input, a positive voltage into the inverting input, you will get a negative voltage on the output. If you put a positive voltage on the non-inverting input, you will get a positive voltage on the output, generally. So here is the model of what's happening inside the op-amp. So this is the op-amp package outline, and I've neglected showing that it's powered, but lots of times in schematics you won't see the power connections to the device, but it's very important not to forget to power up your device. So there is probably a plus 15 volts and a minus 15 volts also connected to this op-amp circuit. So this is the model, what's happening inside. You have your inverting input here, see there's a minus sign, and your non-inverting input here, and then there's an input resistance between these two pins. The input resistance is very, very large. It's almost an open circuit. And then you have the output here. There's an output resistance which is very low, because ultimately this device can be able to supply a lot of current, whatever it's rated for. And then you have your voltage controlled voltage source internally, which depends on the voltage that's across these input terminals. So the A there is called the gain. It's called the open loop gain, and it's somewhere on the order of 10 to the 5th or 10 to the 8th. So whatever the difference is in voltage here, there will be a gargantuan gain, and that's the output, in theory. I'm going to show you where it deviates from theory here in a moment. So the output current that the device puts out is going to actually be the current from the power supply. So there's a so there would be a current coming in from your, say, your plus 15 volts, often called VCC, by the way, and then there will be a current coming in. I'll call it I negative and I positive. There'll be a current coming in from your negative voltage, maybe it's sometimes called VEE, and then there's a current I1 and a current I2 coming into the device, and then there's a current output. So 4 currents coming in, 1 current output. So the amount of current that's going to come in here is going to be very, very small, because you can see it's a very large resistance, and so all of the output, the gain, is really coming from these power supplies right here. So this op-amp device is actually useless by itself, but we have to understand its behavior first, and they're only good for us when we put circuits around it, elements around it, resistors, capacitors, inductors. When we make a circuit around the op-amp, it becomes a useful device to us. In this chapter, we are only doing resistors around the op-amp. It's fundamental to you understanding how the op-amp works. And we're also staying still in the DC world. Very soon now we're going to enter the AC world, and it will be interesting with capacitors and op-amp circuits. So open loop gain is A. Book didn't do a very good job defining open loop, but open loop basically means there's nothing connected around here, like nothing from the output is connected back to the input. Closed loop means that you must have something connected to the output, and you will connect part of the, you will have an output, and then you'll connect something back to the inverting input to give feedback. Feedback makes your device stable, makes it behave properly, which we'll talk about more in the future, but not quite yet. But just understand that open loop means nothing is connected around the amplifier, and closed loop means that something is connected back into from the output back into the inverting terminal, giving it some feedback. So the output voltage, open loop, this is open loop, is A times that difference voltage. So I said the gain was very high, like 10 to the 5th to 10 to the 8th, something like that. The gain is very, very high. But in reality, if I put 1 volt into my amplifier, I'm not going to get 10,000 volts out of my amplifier. What you are going to get is only up to the limit of the power supply. So this here they call it VCC and minus VC. So this might be plus 15 volts and this might be minus 15 volts. So your amplifier is going to gain up whatever the input voltage is. Here's the difference shown here, the difference between the terminals. But if it's too much, then you'll just, we call it hitting the rails. So you can only output as much as the power supply is. And actually, if the power supply is 15 volts, you can only hit about 14.3 volts. There's a thing called a diode drop that we haven't learned about yet. So down here you would hit about minus 14.3 volts. You never even get to the 15. So the circuit cannot output more voltage than either of its power supplies. That will get people sometimes if they're not careful. So first, I think example in your textbook is showing about the non-ideal behavior of an op-amp circuit. So here's an op-amp with a circuit surrounding it, and notice it's a 741 op-amp, which is our garden variety op-amp that we'll have in the lab. And then you replace the op-amp right here with its model. So here's, hopefully you see it in here, but the model is, this is the part that's the model right here. So if you look back, you'll see that that's the model for the op-amp, and then everything else is connected around it, as you see here. So your book analyzes the problem. It does KCL at this node and KCL at that node and solves for the output voltage and solves for the output current. I don't need to run through the KCL on it because you know how to do this kind of a circuit. But what you'll find out is that V out, this is V out over here, over V source, here's our V source, equals minus 1.999992. It actually has to do with the ratio of this resistor to this resistor, and there's a negative sign there, which means the signal will be inverted. If I put 1 volt in, I will get minus 2 volts out. If I put minus 1 volt in, I will get plus 2 volts out, approximately. I won't quite get there because I'm showing the non-ideal behavior of this op-amp. The voltage at node 1 turns out to be this, which is a very, very small amount of voltage. It's in the microvolts. And that's a consequence of the fact that there's almost no current in this branch right here. That means not much of a voltage drop across that internal resistance. So that node is actually very close to 0, just slightly above 0. And then the output current, or the I here, there's no load connected up, but this current right here turns out to be that amount of current in the milliamps. Plenty of current is being output here, is what it turns out basically. So it's good to expose you of the non-ideal performance of the op-amp. But for all practical purposes and almost all the rest of the circuits that we're going to analyze, we're just going to assume ideal op-amp behavior. For all practical purposes, this is a really good thing to do, and there are very few exceptions, mostly high-performance circuits where you have to consider the non-ideal behavior of an op-amp. So we're going to use the ideal op-amp model. So the ideal model says it has infinite open loop gain. So A is approximately infinity. It can supply whatever you need up until you hit the rails, remember. And then we also assume infinite input resistance. So this guy is open right here. And 0 output resistance. So this guy is short. This is open. This is a short, which means I can supply whatever current I need in the ideal world. And I have no input resistance right there. It's open, or I have infinite input resistance. It's open right there. And as a consequence of that, no current is going to flow here either. So those are our ideal op-amp assumptions. And for most cases, they work wonderfully good. So let's go back to that op-amp circuit we had 2 slides back. It's this circuit right here, the one on the left. And apply these rules. So if you always remember these rules and apply the rules, everything else is KCL and KVL. So KCL and KVL stay with us, I think, forevermore. And Ohm's law does too. So the current into both input terminals is 0. That was assumption number 1 from the infinite input resistance. So if I do that, I can say that there's no current here, so that's really not in the circuit anymore, right? That's not in the circuit. And the voltage across the input terminals is 0, which is kind of weird, but it says the voltage difference between here and here is 0. Well, here it's 0 volts because it's tied to ground, so I must have 0 volts right there. So I have 0 volts right there because this one's tied to 0 volts, but no current can flow. So these are kind of weird. Intuitively, they're kind of weird assumptions, but you follow these assumptions and then analyze the circuit from here, and everything will always come out good. So I am going to go ahead and analyze that circuit. So I equals 0 right there, I equals 0 right there, and I have 0 volts right there, and those are applying my ideal op-amp assumptions. So oops. Here is a generic version of the circuit let's go ahead and do this one first with numbers before I do it without numbers. So if I analyze this circuit, the voltage right here is Vs, and the voltage right here is 0. Using Ohm's law, well, let's start with KCL. KCL says current into this node equals current out of that node. So the current in, I1, this one's called out, or I right here, and there's I out of the node. And there's no I right here, so actually all I have is I1 is into the node equals I, which is out of the node at node 1. And so I go ahead and find I1, which is Vs minus 0 volts, right? Voltage across this resistor over 10 k ohms equals, okay, mind my signs here. Current is going this way. That means plus minus this way. So this voltage minus this voltage is what it is. So that's 0 minus V out. I'm going this way. This is 0 volts. This is that, but I have the sign that way. Over 20k. So I have Vs over 10k equals minus V out over 20k, and you find out that V out actually equals minus 20 over 10 V source, which equals minus 2 times V source. So this was the problem we had as a non-ideal op-amp right there, and we found out there that V out over V source wasn't quite minus 2. It was minus 1.9999699. But if I make my ideal op-amp assumptions, then I get that V out over V source equals minus 2. So this is the ideal assumptions, and when it was non-ideal, we had minus 1.999969 or something like that. So that's the difference between ideal and non-ideal. So that's why ideal op-amp assumptions are really quite close enough for us. Okay, so these next few slides, we're just going to go through standard configurations of op-amp circuits. They have names for them. So let's just go through them. First one is the inverting op-amp. This is the formula for its output as a function of its input and its resistors. Standardly, we call this resistor right here the feedback resistor, because this is the resistor that's connected between the output and the input. So a portion of this output voltage comes back and is subtracted from the input voltage. That's how feedback works. This is negative feedback. It keeps the circuit stable. More on that in the future, as I said. So let's go ahead and derive the general case here. I have a V in, a V out, an I1, and I2. I apply my assumptions. 0 volts here means 0 volts there, means 0 volts right there, because the voltage here has to be the same, because there's no voltage difference here. There's 0 volts between the terminals, so these voltages have to be the same. So I do KCL at, this is just like the problem I did a moment ago, at node 1, but I'm doing it generically. So I have I1 equals I2, current in equals current out, no current goes in to the op amp, so that's V in, that's a V1, but we know V1 is 0. V in minus 0 over R1, sometimes that's called R in, equals, minding my signs here, this voltage minus this voltage, which is 0 minus V out over R feedback, and rearranging and solving for everything, you get this. So as my example, if V in, this is what you're going to end up doing in the lab. If V in is 1 volt, V out will be minus RF over RI times 1. If V in is 2 volts, V out will be whatever that gain, that's actually called the gain, the op amp gain, times 2, whatever it is. So that's the inverting amp. It changes the sign of the output. So here's an example, a little bit trickier, not too much, but the one thing to notice about it is that the voltage at this terminal is at 2 volts. There's still no current. I is still 0 going in there, but if B is at 2 volts, then A is also at 2 volts. So let's analyze the circuit. So I have current going in, I1, I2, VA, V out, 6 volts. Okay, so I1 equals I2, plus minus signs there. So 6 volts minus, oh, what's at VA? VA is at 2 volts. 6 minus 2 over 20k ohms equals VA, which is at 2 volts, minus V out over 40k. So 4 over 20 equals 2 minus V out over 40k. So 40k over 20k. Oh, do the math. 40k over 20k times 4 equals 2 minus V out. I'm going to divide by 4 on this. 40 over 20 equals 2 over 4 minus V out. Sorry, somebody just talked to me. I had to pause it for a moment. Where was I? 40 over 20 times 4 equals 2 minus V out. So I divided by 4 on both sides. V out over 4. Why would I even bother to do that? 4 times, this is 2 equals minus V out. So V out equals minus 8. No, don't drop my terms. Sorry, silly algebra mistake. Just got because I got distracted for a moment. So it was 40 over 20 equals 2 minus V out, and so that's 4 times 2 equals 2 minus V out, And so that's 8 minus 2 equals minus V out. So V out equals minus 6. So basically what you had, it was an inverting op-amp. This inverting op-amp had a gain of minus 2, but you had an offset right here of plus 2 volts. And so you got the negative output here. But anyway, you can analyze it just the same with the same KCL rules. Okay, the next op-amp type we're going to look at is called the non-inverting amplifier. The main difference to notice about this one is that the input voltage, the input signal, is now on the positive terminal. In the inverting op-amp, the input signal right here is on the non-inverting, or on the inverting terminal. See, this is on the inverting terminal, and the non-inverting amplifier has the input signal on the non-inverting input terminal. However, you must still have feedback in this circuit. If you do not have feedback, you will just experience a bunch of gain and hit the rails, and that's what will happen. So let's look at the non-inverting amplifier. Now I'm going to show you one way that this is often drawn. I wonder if I could do this. Do I have any other choices in my colors? Not really. Okay. So it's drawn with all of these connections here, but in reality you often see it drawn this way. This is your V in, and ground. And then here's your V out. So you do not have to show this physically connected, but it is physically connected. They are at the same potential. They're both at ground. And V out, sometimes it's drawn this way, is referenced to ground. So it is always the voltage over your zero reference place. Don't be fooled. Sometimes you see V in, sometimes you see it drawn this way also. And this likes to confuse people. Ooh, what am I missing? I'm missing a resistor. Resistor there to ground, yeah. Sometimes it's drawn flipped over this way. This is still the same circuit, and this is still your non-inverting amplifier. So anyway, let's analyze this problem. So this voltage is at V1. That means this node is also at V1. And we notice that this voltage right here is at 0. We put our current markings here, and then we do KCL at that node. I1 equals I2. So that's 0 minus this voltage. Well, this voltage is V in, right? This voltage equals V in, which is VI. VI means V in, over R1 equals this voltage right here, which is V in minus V out over R feedback. So then you do the algebra and you will get this formula. So V out is 1 plus the ratio of the feedback to the input resistor times the input voltage. And of course that's often written as this, which is a kind of a transfer function form. So you just see the gain. That's a 1. That's supposed to be a 1. So this is just the op-amp's gain, the circuit gain. Op-amp gain. That will be the gain of the circuit. So that's the non-inverting amplifier. So a positive voltage in gives a positive voltage out up until the point that you hit the rails. So the next op-amp circuit that we're going to look at is this one right here. It's called the voltage follower. This is the circuit right in here. And it's often connected between circuits. So this is some stage here. It can be an op-amp circuit. And this is some stage over here. It could be another op-amp circuit. But what that does, since the current going in, IN, is 0, but the voltage that's here is the same as the voltages here, and it's the same as the voltage that's here. That means you get the voltage back out over here, but the op amp can go ahead and supply a bunch of current to this next stage. And then, like, maybe this next stage needs a bunch of current, but it won't pull down this first stage or load this first stage. So it's used to isolate the second stage from the first stage, or a second circuit from a first circuit. But we can go ahead and analyze it by itself. Notice the feedback is connected to the feedback where it's supposed to be. There's some voltage V in there from that first circuit, and there's some voltage V out over here. No current in and no current out. Gee, you know, it's kind of, can't even write the equation. So V in is here, which means V in is here, which means that V in is right here, which means that V in equals V out. Or V out over V in equals 1. So unity gain amplifier. It isolates the second stage from the first stage because this op amp can supply a bunch of current over here. So maybe this first circuit can't supply a bunch of current, it just has a voltage output. So that's what they're used for. A summing amplifier. So this is actually kind of a variation of a inverting amplifier. So notice that this voltage right here is at 0 volts, and I can have if I write KCL, I have KCL I1 plus I2 plus I3, which is I right here, equals the current going in equals the current going out, equals I. So now we go ahead and we write Ohm's law for each one of those currents. We've already written KCL. So it's V1, what's this voltage minus this voltage is the voltage drop here. So I can get the current. So V1 minus 0 over R1 plus this one, which is this voltage minus this voltage. V1, V2 minus 0 over R2 plus, and surprise, surprise, same thing there, V3 minus 0 over R3. And that equals 0 minus V out over feedback resistor. So, right, by virtue of the way I drew my arrows, it's this voltage minus this voltage gives me the voltage drop there. So that's this voltage minus this voltage, which is 0 minus V out. So then I go ahead and do the math. And multiplying both sides by our feedback, then you get this equation down below, the final result. So what you're doing then is that you're taking with whatever gain, by the way, you don't have to make that a gain. You can make the feedback resistor be lower than the input resistor. And so you could have a fraction of V1 plus a fraction of V2 plus a fraction of V3 all summed up together to be the output voltage. So this is the difference amplifier. This one is actually a really useful amplifier for a lot of small signal applications, because what it will do is, since you're having to use the difference in the two signals right here is what is subjected to the gain. So, but we're going to set this up to be a difference amplifier. So this signal will be subtracted from this signal. The parts that are the same will be subtracted. So it will reject signals that are common to both, like noise, or maybe some 60 hertz noise is riding across the signals. So and it will subtract out the part that's common and only apply your gain to the part that you're interested, which is the difference between the two signals. So again, we start with KVL or KCL at these nodes, node A and node B. But right now I really can't make any assumptions other than VA equals VB in this circuit. I don't know anything else. It's not at a voltage or at zero. So I just have to go and write KCL at this node and KCL at that node and recognize that VA and VB are the same. So if I do it at VA at that node, I get V1 minus VA over R1 equals VA minus V out over R2. And then at VB I do the same thing, but I recognize that VA equals VB. This voltage equals this voltage, and so I will get V2 minus, I'll say VA over R3 equals VB minus 0 over R4, right? VB minus 0 over R4. Oops, so it's VA, so A equals B. So I now have two equations. I have V1, V out, and just a V2 and still VA over here. So I work with these two equations. I get rid of my VA, substitute it, or get VA will cancel out, and I will ultimately end up with an expression that looks like this. And you don't need to spend YouTube time doing the algebra, I don't think. I set up the KCL for each one, and then it's a matter of just doing crunching the numbers. Now, however, usually this circuit is not operated this way. It's not giving me very useful, intuitive result here, because it's saying that I have a difference on the output, and so some ratio of V2 minus some ratio applied to V1. So how this circuit is actually used, you end up saying R1 over setting your resistor values, R1 over R2 equals R3 over R4. So you pick your resistor values to be the same on both the top part of the circuit, the inverting part of the circuit, and the non-inverting part of the circuit. You pick these resistors to be matched like that. When you do that, you will then get V out equals R2 over R1, 1 plus R1 over R2, and 1 plus R1 over R2, because R3 and R4 are the same, V2 minus R2 over R1, V1, and this cancels, and you get R2 over R1, V2 minus V1 is what V out is. So V out is indeed the difference of the two input signal voltages. And so this is called an instrumentation amplifier, and it's very, very useful. And especially if you're trying to detect as an example, let's make V2 be 0 and V1 is some tiny little signal that you want amplified, but both your ground signal and your ground and your V1 have some kind of a noise from electromagnetic interference, both showing up on both ground and this signal. So if you use this difference amplifier, you can get rid of the electromagnetic noise that's showing up on your voltage signals. So that's the difference amplifier. This is kind of a short chapter in a way, just learning these op amps. This is the summary of the op amp circuits at the end of your chapter. These are, well, the inverting, the non-inverting, voltage follower. These circuits should be committed to memory. You should just automatically memorize the equation for V out as a function of Vn for these circuits. They will occur over and over and over again. In later chapters we'll put capacitors in here, and it will make integrators and differentiators. But right now we're just looking at the DC signals. You should memorize these relationships. Memorize how to derive these relationships so that when you see a circuit like this, you could rederive it should you need to. So that's all for this video. The next video I'm going to go ahead and just do multisim using an op-amp circuit.